Welcome back. This video is going to deal with the Chapter 8 portion on solutions, acids, and bases. And I'm just going to go through a few of these questions pretty quickly and then go through a couple of terms with some pictures here so you can get an idea of what's going on. So during the formation of a solution, energy can be released or absorbed. We've used those terms endothermic and exothermic several times throughout the semester. Two components of a solution. We have the solvent and the solute. The solvent is what determines if the solution is a liquid, a gas, or a solid. For example, air being a gaseous solution because it's dissolved in nitrogen, or sweet tea being a liquid solution because it's dissolved in water that's in a liquid state. The solute is what has been dissolved into the solvent, so it's the thing that's being dissolved, while the solvent is the thing that there is more of in the solution. The three ways that a substance can dissolve in water, and this is where I want to show you a picture here summarizing everything, are ionization, dissociation, and dissolution or solvation. These first two create electrolytes, while the last one creates a non-electrolyte solution. And in our first example, hydrochloric acid, which starts as hydrogen chloride, is dissolved in water and it's pulled apart, separated into hydrogen ions and chloride ions. Second substance dissociates. Sodium chloride is an ionic salt, which means it's composed of a positive and a negative piece. When you put it into water and dissolve it, those ions are separated from each other, and instead they associate with the water molecules, and it also forms ions, positive sodium, negative chloride, which is why both of these solutions will conduct electricity. The third type is dissolution or solvation is the term that I would usually use. For example, sugar, C6H12O6, glucose, will dissolve in water, but it will not conduct electricity. It is a non-electrolyte, and that's because when it's dissolved into water, it doesn't actually separate. Instead, if this represents the sugar molecule, then the water is just sort of all surround it without actually separating its chemical bonds. So the molecules of sugar will separate from each other, allowing the water to surround it, but the sugar molecule itself does not actually break apart, unlike ionization or dissociation. Alright? The ways that a substance can dissolve in water: ionization is a chemical change because it breaks down one compound and produces ions out of it, which is not usually a reversible process. If I dissolve salt into water, I can recover this salt by boiling off the water or distilling everything so that the water comes off as steam, and the sodium chloride recondenses at the bottom in a crystal. If I do the same thing with sugar water, the sugar will eventually boil down so that it's more concentrated and it will precipitate as a solid, and then you could boil off the water. Now, of course, sugar, if you kept heating it like that, would just decompose and caramelize. But you can't do the same thing to an ionized process. So hydrogen chloride dissolved into water makes hydrochloric acid. You're not going to reverse that process. Alright? Solution concentration can be represented a number of ways. The most common way when you're looking at a solubility graph, which is the more important way, is grams of the solid or gas out of 100 grams of water. And those are the graphs that look something like this. They have lots and lots of lines going across them. Some of them are steep, some of them are curved. One or two of them might go down because those are the gases. And it will say grams out of 100 grams of water and temperature on the bottom axis. In reactions in chemistry, usually something called molarity or M, but that's not particularly important until you get to chemistry. Moving along, this part is important for physical science, is solution concentrations. Relatively speaking, they can be unsaturated, saturated, or supersaturated. Referring back to that same graph, if I just make a simple curve over here, any point on this curve is what we consider a saturated solution. So for any value of T and gram per 100 grams of water. Say this is 50 degrees and this is, let's just call this 20 grams. No particular reason. So anywhere along this curve is saturated. If for the same temperature you fall below the curve, you are unsaturated because you could still dissolve this much more. And anywhere above the curve, again at the same temperature, represents a supersaturated solution, and whatever this excess is will come crashing out as a solid precipitate if you give it half a chance. Okay. H+, those are called the hydrogen ions, which are produced by acids when you dissolve them in solution. Examples of acids include hydrochloric, sulfuric, and nitric, hydrofluoric, all sorts of things. Hallmark is they start with hydrogen. And when you dissolve them in solution, they will ionize to form a hydrogen ion in solution, and that's the part that determines that it's an acid. Anything that makes these hydrogen ions is considered an acid, with a pH less than 7. Bases do the opposite. They will produce hydroxide ions in solution. So bases are things like sodium hydroxide, lithium hydroxide, calcium hydroxide, all sorts of things. Magnesium hydroxide. Now there is one base that does not look like a base according to this rule, and it is ammonia. But ammonia, when dissolved in water, actually forms ammonium hydroxide, which is why it acts like a base. Just some things to remember. Indicators, most important, are litmus paper and phenolphthalein. Litmus paper, bases will turn red paper blue, and acids will do the reverse. Phenolphthalein, bases turn the solution red or a bright pinkish color. Acids turn it colorless. Neutral litmus paper is one that we used in our lab this year. So I'll just add it off to the side. Neutral litmus. Acids are red, bases are blue. Alright. Some general properties of bases, or alkaloids is another word for them. They are slippery to the touch, they are bitter in taste, they are caustic, meaning they will burn, they produce hydroxide ions, and they turn litmus paper blue. This is why a lot of bases feel slippery, is because they make your outer layer of fat cells turn into a soap compound, because soap is actually produced from animal fat reacting with a base, caustic soda lime. The reason they tend to taste bitter is most alkaloids have actually evolved to be poisonous to animals. It's a defense mechanism of plants. They're used as insecticides to keep animals and insects from eating the plants. They're used to keep larger animals from chewing on the plants. So they've evolved as poisons. And so most alkaloids tend to be poisonous to people, and so we've sort of evolved to taste them and be very sensitive to those bitter tastes and not like them as much, because most bitter things, alkaloids, tend to be poisonous to some extent. Now acids, on the other hand, taste sour, they are corrosive, they produce hydrogen ions, They will react with metals, not all metals, but reactive metals like the alkali, the alkaline earth, to produce hydrogen gas, so it will literally bubble, and they turn litmus paper red. And stomach acid in your digestive tract is hydrogen chloride or hydrochloric acid. So we've evolved to handle acids pretty well. Our stomachs are lined with cells that are acid resistant, but it's so corrosive in the stomach that it actually replaces them once every week approximately. Alright, tune in for the next video to go through the part 2 solutions.